So I really struggled with differential equations at A level. I think just the phrase differential equation sounds a bit scary, but I think overall, when you get enough practice at them, I think there are actually worse things that you can be asked at A level. I don't think they're actually that bad. So here's an example to show you how to solve differential equations. So we have dy over dx is equal to yx squared. And essentially, there are three steps to solving a differential equation, okay? So firstly, one of the things that we don't like about differential equations is on this side of the equation, for example, we have this y term here, but we also have this x squared term as well, and we don't like this. So the first step is we have to rearrange the equation to get all of the y and dy terms onto one side of the equation and get all the x and dx terms onto the other side of the equation. So we need to split up the x and y terms. And then secondly, we need to integrate both sides of the equation after we've done this rearranging. And then thirdly, you don't always have to do this. You only need to do it if the question asks you. The question may ask you to rearrange this equation that you've come up with to make y the subject, so therefore you kind of get it in the familiar format of that y is equal to a function of x. But as I said, you only need to do this if the question asks you. Sometimes it might actually be impossible in order to rearrange it into this form here. Okay, so let's go through this example here to show you how solving differential equations works, and we're going to go through the three steps one at a time. So let's start with the first step, where we need to rearrange this equation here to get all the y terms on one side and all of the x terms on the other side. And what we're going to do, we're going to get all the y terms on this side and all of the x terms on this side, okay? So let's first focus on this y term here. So we want to get this onto the other side. So what we're going to do is we're going to divide both sides by y, so therefore this y here will cancel out, and then on this side it will now be 1 over y, like this here, and then dy over dx, and this is equal to x squared, okay? So we've done the y part, we've got all of the y terms on this side, so now we just need to get all of the x terms on this side, so we need to get dx onto this side here. So the way that we're going to do that is we're going to multiply both sides by dx, so this cancels out here, and it leaves us with 1 over y dy is equal to x squared dx. And here we've got all the y terms on this side and all of the x terms on this side. So we've done the first step. I just want to mention really quick, I don't think it's that important, but to get from this equation to this equation, we're actually not multiplying both sides by dx. That's not mathematically how it works. But at A level, I think it's fine to think about it like that. Okay, so we're left with this equation here, and now we need to do the second step, which is that we need to integrate both sides of this equation. So this is going to look like this here. So we've added these integration symbols in front of both of these sides of the equation. And what's important about both of these sides is what we're integrating with respect to. So on this side it's dy, so we're going to be integrating in terms of y, and on this side is dx, so we're going to be integrating in terms of x, okay? So let's consider these sides individually. So let's start with this integrating this 1 over y with respect to y, and we talked about in the first video in this chapter called Integration Basics, we talked about the fact that when we integrate something like 1 over y or 1 over x, it's equal to the natural log of the modulus of y, like this here. So this is this side integrated, and then this side integrated the integral of x squared with respect to x. This is just basic year 1 integration. This is equal to 1 over 3 x to the power of 3, like this here. So we've integrated both sides here. Just remember as well to include the constant of integration. It doesn't really matter what side you put it on. You can put it on this side instead if you want to. I've put it on the x side here. Okay, and then for the third step, as I said before, you won't always have to do this, but the question might ask you to rearrange to make y the subject. So let's say that this is an exam question, they have asked you to do this, so therefore we would need to rearrange this to make y the subject. And as on this side we've got the natural log of y, what we're going to do for both sides of this equation, we're going to make them powers to base e like this here. And what's useful about this is on this side we've got e to the power of the natural log of the modulus of y. And if you remember the laws of logs, if you have e to the power of the natural log of something, so for example x, this will just be equal to x. It will cancel down. So therefore this equation here will cancel down. So this side here will just be y like this. So you can kind of get rid of this modulus as well. So this side here will just be y, and this will be equal to e to the power of 1 over 3 x to the power of 3 and then plus c. You can actually further simplify this because this plus c in the power, what you can do, remember the laws of indices, is when you have two things that are in a power that are added together, what you can do is you can split this up into two separate powers by multiplying them together like this here. And what you can do with this e to the power of c, as c is a constant, e to the power of c is also a constant. So what you can do is you can make a substitution, say something like a is equal to e to the power of c, and you could rewrite this as y is equal to a e to the power of 1 over 3 x to the power of 3. You don't have to do this, but this is a bit of a neater format than this here. And then this here is the final answer, and we've solved the differential equation. So as I said before, I think when you do enough example questions, past paper questions, I think when you get kind of used to these kind of 3 steps, I think these questions aren't too bad. Okay, so here's an example question from a past paper where we need to solve the differential equation dy over dx is equal to yx squared cos of x. Now we're also given this information here that y is equal to 1 at x is equal to pi, and this is important, but we don't need to worry about this at the start. This we focus on at the end, so I'll talk about this later. We first need to actually focus on solving this differential equation here. Okay, so let's consider these steps from before. Firstly, we need to rearrange this to get all the y terms on one side and all of the x terms on the other side. So if we focus on this y to start off with, so if we divide both sides by y, so we get rid of this y here, it becomes 1 over y dy over dx on this side here, and then we want to move this dx onto this side here, so therefore we multiply both sides by dx, so we get that 1 over y dy is equal to x squared cos x and then dx. And then we need to do the second step, which is integrating both of these sides. So if we first consider this side here, 1 over y dy, this is the example that we talked about before as well. This is the natural log of y. You don't actually need to worry about putting the modulus signs here for this question because it tells you that y is bigger than 0, so you don't need to worry about using the modulus signs in case y is a negative value. And then if we focus on this side here, the integral of x squared cos x, so we have two functions that are multiplied together, so therefore we're going to use integration by parts. Now I did a video in this chapter already on integration by parts, so go back to that if you need a reminder. I've given you the formula for integration by parts here because it's given to you in the formula booklet, and because one of the functions here is x squared, this is one of the examples where we need to integrate by parts twice. So remember, for integration by parts, we call one of the functions here, we call one of them u, and then we differentiate that function, and we call the other function dv over dx, and then we integrate that function. And when we're using integration by parts, we like to call x or x squared, we like to call this u, and differentiate this, and then we're going to call dv over dx the other function cos x. So if we first differentiate this, it's going to be du over dx is equal to, and if you differentiate x squared, it's equal to 2x, and then if we integrate this here, it's going to be v is equal to, and when you integrate cos x is equal to sin x. So therefore, if we look at the formula for integration by parts, it's uv, so u is x squared and v is sin x, it's going to be x squared sin x, and then it's minus the integral of v du over dx, so v is equal to sin x and du over dx is equal to 2x, so this is going to be minus the integral of 2x sin of x. I've taken the 2 out of the integral like this here, so we're focused on integrating this x sin x, and because we have this x here and we have these two functions multiplied together, we're going to use integration by parts on this again. So we're going to call one of the functions u and one of the functions dv over dx, and as we talked about in the integration by parts video, we like to call u x and the other function dv over dx. So u is x and dv over dx is sin x. So if we differentiate this, it's going to be du over dx is equal to, and if you differentiate x, it's just equal to 1. And then if we integrate this dv over dx, it's going to be v is equal to, and then when you integrate sin x, is equal to minus cos x. Okay, so remember we still have this x squared sin x minus 2 here, and then we're integrating this, so we put the rest in brackets. So it's going to be uv, so u is equal to x, v is equal to minus cos x, so it's going to be minus x cos x, and then it's minus the integral of v du over dx, so v is minus cos x and du over dx is 1, so it's going to be minus cos x. But because we've got minus the integral of this and it's minus cos x, we can cancel out the minuses here, and therefore we will be left with plus the integral of cos x, like this here. And then we can simplify this because the integral of cos x is sin x, and then we can expand this bracket here, so this minus 2 multiplies this minus x cos x to leave us with plus 2x cos x, and then this minus 2 multiplies this sin x to leave us with minus 2 sin x, and this here is the answer to this integral here. So therefore on this side of the equation, it's going to be these terms added together. So it's going to be x squared sin x plus 2x cos x minus 2 sin x, and then remember the plus c on the end. Okay, so we've got this equation here, and now we're going to focus on this information that y is equal to 1 at x is equal to pi. Now, for differential equations, there are two different types of answers. There's the general solution and there's the particular solution, okay? So the general solution is actually this answer that we've got here. And the general solution has plus c in it, and what's important about the general solution is we don't know what plus c is, so we just call it c. And the particular solution is where we actually know what c is and we can find it out. And in this case, we can find the particular solution because we're told this point here that y is equal to 1 at x is equal to pi. What we can do is we can sub in these y and x values and then rearrange to find c and then plug this in to get the particular solution. Okay, so let's do that. So we're going to sub in y is equal to 1 and x is equal to pi into this equation here, like this, and we can do some simplifying here. Firstly, the natural log of 1 here is just equal to 0, and then here sin pi is equal to 0, so this term here will just cancel out. Same with this term here, we've got sin pi, so this will just cancel out. Cos of pi is minus 1, so this here will be minus 2 pi, and then we have this plus c on the end. And now what we can do is move this minus 2 pi onto the other side of the equation to get that 2 pi is equal to c. So therefore the value of c is 2 pi. So therefore the particular solution to this equation is this here, where c is equal to 2 pi. So that's the difference between the particular solution and the general solution. It's just with the particular solution we know what c is, and this here is the final answer. The question doesn't ask us to rearrange it to make y the subject, so therefore we can leave this side here as the natural log of y. Okay, so here's another differential equation question from a past paper. Okay, so for part A, we need to find the integral of 9x plus 6 over x, and this is really easy because we have one term in the denominator and 2 in the numerator, so therefore we can split up this fraction like this here, and if we look at this, these x's will cancel out and just leave us with 9 here, so it's going to be the integral of 9 plus 6 over x. So we have two terms here that we need to integrate, so let's consider them individually. So if we start with the integral of 9, this is going to be equal to 9x, and then if we consider the integral of 6 over x, I've taken the 6 out of the integral like this here, so it's the integral of 1 over x. This is just going to be the natural log of x, so the 6 at the front is going to be the 6 natural log of x. Like before, as x is bigger than 0, we don't need to worry about the modulus, so therefore this integral, if we add these terms together, it's going to be 9x plus 6 natural log of x, and then remember the plus c on the end. Okay, and then for part B, we're told that given that y is equal to a at x is equal to 1, we need to solve this differential equation here, and we need to give our answer in the form y squared is equal to gx, so y squared is equal to a function of x. Now again, we're given this information here to figure out a particular solution, so we don't need to worry about this at the start. What we first need to do is solve this differential equation here. So remember the steps. Firstly, we need to get all the y terms onto one side and all the x terms onto the other side. So we have this y to the power of 1 over 3 here that we need to bring onto the other side. So we divide both sides by y to the power of 1 over 3. So it becomes on this side 1 over y to the power of 1 over 3, and then dy over dx, and then we bring this dx onto the other side, so we multiply both sides by dx, so we get 1 over y to the power of 1 over 3 dy is equal to this 9x plus 6 over x dx. And then the second step is we integrate both sides. Now I've written this here as y to the power of minus 1 over 3, because remember, when you have 1 over something, remember your indices laws, you can write this as a minus power. So we can write this as y to the power of minus 1 over 3, and this is easier to integrate. So we'll start with this. When you integrate this, this is just year 1 integration. This power goes up by 1, so it's going to be to the power of 2 over 3 now, and we also divide by this power, so it's going to be 3 over 2. And then if we focus on this side, this is what we figured out in part A, this integral of 9x plus 6 over x is equal to 9x plus 6 natural log of x, and then the plus c. Now it tells us it wants us to give our answer in the form y squared is equal to a function of x, so we need to make this side here y squared. So firstly, let's get rid of this 3 over 2, so divide both sides by 3 over 2, so this here goes away. Remember, when you divide by 3 over 2, it's the same as multiplying by 2 over 3, so we need to divide these two terms here by 2 over 3, so it becomes 6x plus 4 natural log of x here, and we still got this plus c on the end. And in order to turn this y to the power of 2 over 3 into a y squared, we're going to cube both sides of this equation like this here. And then if you see this, remember that when you have a power to a power like this here, this 3 cancels out with this 3 here to leave us with y squared. So therefore, in this format here, it's y squared is equal to 6x plus 4 natural log of x plus c to the power of 3. Okay, so we've got it in this format here, so all we need to do now is use this point here in order to find the particular solution and the value for c here. So if we sub in y is equal to a and x is equal to 1 like this here, so 8 squared is 64, and then 6 times 1 is 6. This natural log of 1 will cancel out, so it leaves us with this here, and we've got this power of 3 here, so if we take the cube root of both sides, so this power of 3 goes away and it's just 6 plus c, and then the cube root of 64 is 4, and then move this 6 onto the other side, so we get that c is equal to minus 2. So therefore the particular solution to this differential equation is y squared is equal to 6x plus 4 natural log of x minus 2 to the power of 3. Okay, so here's another question on differential equations that I've adapted from a past paper question. Okay, so for part A, we need to express 3 over 2x minus 1, x plus 1 as partial fractions. Now, we talked about partial fractions in a video back in year 2 of chapter 1, so go back to that if you need a reminder of how they work. But we're going to split this up into two partial fractions because we have two brackets in the denominator here. So one of the fractions is going to have the 2x minus 1 denominator, and the other is going to have the x plus 1, and we're going to call the numerators a and b, and we need to find what a and b are. So firstly, what we're going to do with this equation here is we're going to multiply all the terms by this denominator here, so these two brackets, 2x minus 1 and x plus 1. So if we first focus on this term, this will just cancel out this denominator here and leave us with 3. If we focus on this term here, this 2x minus 1 denominator will cancel out with the 2x minus 1 bracket and just leave us with a multiplied by x plus 1. And then this term here, the x plus 1 denominator will cancel out with this bracket and leave us with b multiplied by 2x minus 1. Now, there's two ways that you can solve partial fractions from here. You can either use substitution or you can equate the coefficients. I'm going to use substitution because I just think it's easier. So what we need to do is we need to make substitutions to make these two brackets equal to 0. So if we start with this bracket here, x plus 1, if you sub in x is equal to minus 1, it will make this bracket equal to 0, and therefore this term will cancel out and we'll be left with an equation that doesn't have a and only has b. So if we sub in x is equal to minus 1, this side here will still be 3, and then it will be b, and then 2, and then we sub in the minus 1 for x here, and then minus 1 like this here, and then this bracket here is minus 3, and then if you divide both sides by minus 3, you get that b is equal to minus 1. So we figured out b, so now we need to figure out a by making this bracket here equal to 0, and we use the substitution that x is equal to a half, so this term goes away, so we're just left with 3 is equal to a, and then a half plus 1 in the bracket. This bracket here will simplify to 3 over 2, and then we divide both sides by 3 over 2 to get that a is equal to 2. So therefore we found a and b, so therefore to split this up into partial fractions, it's going to be 2 over 2x minus 1 minus 1 over x plus 1. Okay, and then for part B, we need to solve the differential equation here and show that v can be written in this format here. We're also given this information that v is equal to 3 when t is equal to 2. This is to do with finding a particular solution, so we don't need to worry about this at the beginning. We first need to focus on solving this differential equation. So let's do that. So this equation here is not to do with y and x, it's to do with v and t, and if you want to, you can think about the v being the y and the t being the x. So remember how to solve a differential equation, the steps. What we first need to do is put all the v terms onto one side of the equation and all the t terms onto the other side. So if we focus on this v first, we need to move this onto this side, so we're going to divide both sides by v, so it becomes 1 over v dv over dt on this side here, and then we need to move this dt onto this side, so it becomes 1 over v dv is equal to 3 over 2t minus 1 t plus 1 and then dt. And remember the second step, we need to integrate both sides of this equation. Now this fraction here is what we figured out in part A. We figured out that we could split it into these partial fractions, so therefore we can write this integral like this here on this side, and this is easier to integrate instead of this. Okay, so we need to integrate both sides of this equation, so let's start with this side, this 1 over v, so this will be the natural log of v. We're told that v is bigger than 0, so therefore we don't need to worry about the modulus symbols here, so we can just write it as the natural log of v. So on this side we've got two terms, so let's consider them individually. So let's start with this 2 over 2t minus 1. I've taken the 2 out of the integral like this here. Now we talked about how to integrate something like this in the second video in this chapter called integrating f of ax plus b, so go back to that if you need a reminder. But the way we integrate this is this here, this 1 over 2t minus 1 is of the form 1 over x. We've talked about that when we integrate this is equal to the natural log of x. So when we integrate this, this is going to be equal to the natural log of, instead of x, it will be this denominator here, so the 2t minus 1. But we talked about in that video that we also need to divide by the coefficient of t, so we also need to divide by 2, so it will be half natural log of 2t minus 1 like this here. And remember the 2 that we took out at the start here, so it'll be 2 multiplied by a half, and this will cancel down to the natural log of 2t minus 1. Again, we don't need to worry about the modulus symbols here because we're told that t is bigger than a half, so therefore there's no way that 2t minus 1 can be a negative number, so we don't need to worry about the modulus symbols. And then if we focus on this minus 1 over t plus 1, so this is similar to this one here as well. It's of the form 1 over x, so it will be the natural log of, and then instead of x it will be this t plus 1. We also need to divide by the coefficient of t, but as the coefficient of t is 1 in this case, it doesn't make a difference. So remember this minus at the front will be minus the natural log of t plus 1. Again, we don't need to worry about the modulus symbols because of this restriction here. So therefore this side here, if we add these terms together, it will be the natural log of 2t minus 1 minus the natural log of t plus 1, and then remember the plus c on the end. Okay, so we're left with this equation here, and we can simplify this because we have these two logs here. So we've got this log minus this log, and if you remember your laws of logarithms, when you have this, you can combine these two logs together by dividing them. So this is going to be the natural log of v is equal to the natural log of this here, and then plus c. And then we can find the value of plus c here by using the fact that v is equal to 3 when t is equal to 2, so we can sub these values in like this up here. And inside this bracket here, we've got 2 times 2 minus 1, which is 3, and then 2 plus 1, which is 3. So this is going to be 3 divided by 3, which is 1. So this is the natural log of 1, and the natural log of 1 is 0. So this is going to cancel out and leave us with the natural log of 3 is equal to c. So therefore, we found the value of c. So therefore, we can write out the particular solution to this equation here as this. Now we need to show that v can be written in this format here. So what we can first do is we can combine these logs together because we've got two logs that are adding together. So remember laws of logs, this means that we can multiply the things inside the logs like this here. So it's going to be 3 multiplied by this 2t minus 1 over t plus 1. And as on both sides of this equation they're both natural logs, what we can do is we can just get rid of these natural logs now and write this as v is equal to 3 times 2t minus 1 over t plus 1, and this is what's required. Okay, so here's one final question on differential equations for you to have a go at. I've slightly adapted this question from a past paper question. I've given you a couple of things here as well. I've given you the integration by parts formula because, as I mentioned before, it's given to you in the formula booklet, so you'll have access to it in the exam. And I've also given you the integral for cot x, which is equal to the natural log of the modulus of sin x. If you don't know, this is also given to you in the formula booklet, and I guess it's a bit of a clue that you'll need it in this question. So pause the video, have a go at the question, and I'll go through the answers in about 5 seconds. Okay, so for part A, we need to express 1 over y plus 1 as partial fractions. So this is just a very easy partial fractions question. Okay, so we can split this up into two partial fractions, one of them having the denominator y and the other one having the denominator y plus 1. And then we're going to multiply all the terms in this equation here by this denominator, so y plus 1. So if we do this for this term here, it's just going to cancel out the denominator and leave us with 1. For this term here, the y here is going to cancel out and leave us with a multiplied by y plus 1, and then for this term here the y plus 1 denominator is going to cancel out with this bracket and leave us with b multiplied by y. And then what we're going to do is we're going to make substitutions to make these terms cancel out and equal 0. So if we start with y plus 1, we're going to let y equal minus 1, so therefore this bracket's equal to 0. And this term here cancels out and just leaves us with b, so it's going to be 1 is equal to minus b, so therefore b is going to be equal to minus 1. And then for this one here, we're just going to let y equal 0, so therefore this here will be equal to 0, and therefore it will be that 1 is equal to a. So therefore, to split this up into partial fractions, it will be 1 over y minus 1 over y plus 1. Okay, so for part B, we need to solve the differential equation sin squared x dy over dx is equal to 2xy y plus 1. So remember these steps for solving a differential equation. Firstly, we need to get all of the y terms onto one side of the equation and all of the x terms onto the other side. So let's first start with this y plus 1, and we want to get these terms onto this side. So we're going to divide both sides by y plus 1. So on this side it goes away, and then on this side it's going to be 1 over y plus 1, and then we've still got the sin squared x dy over dx. Okay, and now what we want to do is we want to get all the x terms onto this side. So let's first focus on this sin squared x. We want to get this onto this side, so we're going to divide both sides by sin squared x. So on this side it goes, and then on this side it's going to be, so remember that 1 over sin squared x is equal to cos x squared of x. So we can write this as 2x cos x squared of x, and then we also want to get the dx dx onto this side as well, so it becomes 1 over y plus 1 dy is equal to 2x cosec squared x dx, okay? And then remember the second step, we want to integrate both sides. Now this fraction here, we showed in part A that it can be split up into these two partial fractions, so that's what I've done here, and this is easier to integrate. So if we first focus on this side and consider these two terms individually, so the integral of 1 over y dy, as we talked about before, is just the natural log of the modulus of y. And then this minus 1 over y plus 1, I've taken the minus out of the integral like this here. So this is again of the form 1 over y, but the y is replaced with the y plus 1, so it's going to be the natural log of the modulus of y plus 1. But remember, we also divide by the coefficient of y, but in this case it's 1, so it doesn't make a difference. And then remember, we have this minus here, so it's going to be minus the natural log of this. So therefore, if we add these terms together on this side, it's going to be the natural log of the modulus of y minus the natural log of the modulus of y plus 1. Okay, so now let's focus on this side of the equation here. So the 2x cosec squared of x. I've taken the 2 out of the integral like this here, so it's the integral of x cosec squared of x. And here we have two functions that are multiplied together, and one of them is x. So this is a really big clue that we need to use integration by parts. So one of these functions we're going to call u, and the other one we're going to call dv over dx. And as we talked about in the integration by parts video, we like to call x u and then differentiate this, and then call the other function, which in this case is cosec squared x. We like to call this dv over dx and then integrate this. Okay, so let's consider this. So firstly, let's differentiate u is equal to x, so it'd be du over dx is equal to, and if you differentiate this is equal to 1, and then if we integrate this here, it will be v is equal to, and we've talked about already in year 2 integration, we talked about it in the first video, integration basics, that when we integrate cosec squared of x is equal to minus cot x. Okay, so let's consider the integration by parts formula. So it's uv, so u is x and v is minus cot x, so therefore uv is going to be minus x cot x. Remember, we need to include this 2 at the front as well that we took out at the start, and then it's going to be minus the integral of v du over dx. So v is minus cot x and du over dx is 1, so this is just going to be minus cot x. So it's minus the integral of minus cot x, so therefore these minuses can cancel out and it can be plus the integral of cot x like this here. And then we simplify this because the integral of cot x is given to you in the formula booklet. It's equal to the natural log of the modulus of sin x, and then we can expand this bracket here with this 2 at the front, so it becomes minus 2x cot x plus 2 and then the natural log of the modulus of sin x like this here. So when we combine this with our previous result, it's going to be this here, the final answer, where we've got all these terms here, and we can simplify this slightly if we want to, because we've got the natural log of the modulus of y minus the natural log of the modulus of y plus 1. So we can combine these using the laws of logs and write this as the natural log of the modulus of y over y plus 1 in a slightly simplified format. So this here is the final answer.